an empty room, probably at my desk, and then post the recording. So I know that's harsh. You're like, really, Mrs. Snipes? Yeah. So I brought this here today to kind of remember all the different types of intermolecular bonds. Remember, intermolecular bonds are weaker than the covalent bonds. This is how you can stick matter together, different molecules or ions and such. Now, when we talk about solutions, this is like a Gen Chem 1 thing. We have actually a solute dissolved in a solvent, mixture solution. Okay, 2 or more components we call the solutes dissolved in solvent. If the solvent is water, we call that an aqueous solution. Now, some of these things you may not consider as solutions, but you just have to have, and actually a homogeneous mixture, a synonym for homogeneous mixture, is a solution. So, go figure. Air, as we're breathing it, actually we have the thing that's greater amount is nitrogen gas, lesser amount, kind of 80-20, oxygen, that makes a solution. Soft drinks, aqueous solutions, we have carbon dioxide, in this case a gas is a solute dissolved in liquid water, the solvent. Hydrogen and palladium. Palladium is there in major amount. It's a solid, and actually hydrogen gas is infused in that solid. When you buy a jar of rubbing alcohol, sometimes I feel like I'm on one of those games where I'm trying to tell you what I'm thinking about and you're supposed to guess. But when you buy a thing of isopropyl alcohol, some of us really like, it's actually pure isopropyl dissolved in water, so it's an aqueous solution. Salt water, sodium chloride would be your solute. Wait a minute. Oh, check this out. Now we have pure isopropyl alcohol, isopropanol, and just a minor amount of water. So that's why water is your solvent. It's not an aqueous solution. Salt water, water is your solvent. Brass, I know it feels weird, but those frozen atoms of different metals actually make it a solution. Brass is, the majority of it's copper, and it's probably different grades of brass, but a common solute metal would be zinc. So whenever we're making a solution, we're taking something in lesser amounts called our solutes and dissolving it in things of greater amount, which is our solvent. But we can kind of think of it stepwise. This says expand the solutes. And actually later on I'm going to say take your solute particles and they have to break their connection with each other if they're going to go ahead and dissolve and be amongst the solvents. Okay? So we are breaking these bonds of the solutes. You have to break the bonds of the solvents and then they mix together. Not only do they mix together, but these bonds are broken, which we're going to see as endoplane, and these bonds are formed, which is actually hexagon. So break bonds, form mixture, form bonds. We can kind of think of it stepwise like that. So this is actually just the sheet. Okay. Now the thing with the asterisks, this says asterisks that you can only have this sort of intermolecular bond if you're dealing with a mixture. Okay, so makes sense. Okay, because for instance, let's pick on this guy down here. Dipole is a polar substance. If it's going to intermolecular bond with something that's non-polar, the other thing's going to be an induced dipole. So dipole, induced dipole means you have 2 or more things in there. Okay. So yeah, dipole, induced dipole, or an ion dipole are all possible mixtures. And then down here, and I probably just blew through this when we were kind of covering the different types of intermolecular bonds. But we have this kind of weird thing called a hydrated salt. And for instance, the copper 2 sulfate likes to have 5 waters of hydration for it, around it, for every 1 formula unit of copper 2 sulfate. So in that case, we do kind of, within a pure crystalline lattice structure of the copper 2 sulfate pentahydrate, you would have some ion dipole because your water molecules. It's a sub. So things that can be either mixtures or pure substances are things we've been kind of talking about up till now, because we haven't been talking about mixtures because we've just been talking about something in pure state. So you could have something that has a hydrogen, what do we say, hydrogen oxygen, hydrogen fluorine, hydrogen nitrogen, and it's no hydrogen bond with itself or something else. Ordinary dipole, that's just polar substances. You could have two different polar substances. You could have a mixture like that. Induced dipole, you could have a mixture or pure substance. Mixture just we have two non-polar things that are going to form intermolecular bonds. So those could go either way. Ion dipole forces, I feel like we kind of have covered these before. Oh, okay. Ion dipole. This is an example of an ion dipole. You might be like, well, water can hydrogen bond, but there's no ion hydrogen bonding. There's an ion dipole, just to kind of remind you. Okay. So sodium chloride, ion, H2O, it's can hydrogen bond, but it's polar. So ion dipole. This is what happens when you dissolve, I guess not sodium chloride, it's potassium chloride in water. I just think this is so cool. We said that those Mickey Mouse things, those are your water molecules. The red thing is the oxygen, it's partially negative. The white things are the hydrogens, they're partially positive. So you can see, and this is called solvation, like solventing. In this case, the sodium chloride crystalline structure. So those partially negative oxygens surround the partially positive potassium cation. And then the chloride ions are taken away by the partially positive ends of the water molecules. They're negative. They're not started, they're negative. So this is kind of what's going on. And again, we have to break these ion-ion bonds, and then kind of over here, we have to break the hydrogen bonds of the water molecules, break those, and then they can form these new ion bonds. This again, now this is a potassium chloride, this is sodium chloride, and trying to emphasize what I've been saying, the kind of, and we learned with Hess's law, it doesn't have to happen in these 3 steps, but if the 3 steps add up to the overall result, then you can think of them stepwise. So here we're breaking the strong ion-ion the strong ion-ion in a molecular bond. Here we're breaking the relatively strong hydrogen bond, dipole-dipole. Okay, and here we're forming those new intermolecular bonds.
I was just thinking about it right now while she was talking. I was really just thinking about it.
Or more, probably. That's a little bit more than that. What? Yeah.
Oh.
No, I'm not actually. Yeah, you're right. Ooh, it's like 40 minutes. But then you do it well there. Yeah. But how many have we already gone through? Like,
We did. I flash because we missed a lot of them.
figure out.
Okay, so break bond, form bond. Dipole, induced dipole would be a situation where you are successfully dissolving something polar and nonpolar together. And as some of you guys already know, polar and nonpolar don't like to mix, but they do mix to a certain extent. Okay. Here's an example of that. I have some videos. So hopefully you guys would tell me an O2 molecule nonpolar, water molecule pretty darn polar. 2. Again, Br2, you probably will tell me nonpolar. And then we have water, H2O. So we have nonpolar, polar. If we go ahead, put the two together and mix them, like the caption says, like dissolves like, and unlike and like, and unlike don't like dissolves like, and 2 unlike things. And we're talking about polarity there. So we have nonpolar, polar, don't like to dissolve. But can you see the coloration here? So that's your water layer, okay, which is polar. And to a certain extent, we have the Br2, which is nonpolar, dissolved in there. Okay, so it does to a certain extent. And how does it do it? Well, you must have the dipole, induced dipole intermolecular bonds for that to happen. This is showing you a couple of compounds. You see oxygen is the red, the black are carbons, and the white are hydrogens. So this is actually showing you it's not hydrogen bonding, but we can see that oxygen has a partially negative associated with it. And then this is actually carbon disulfide. It has this linear shape, which makes it actually nonpolar. Remember, we kind of talked about if your centers of positiveness and negatives coincide, it's actually nonpolar in and of itself. So if you were going to go ahead and get something nonpolar to dissolve into something polar, assuming that this is your solvent, which makes a pretty good solvent, acetone, then you're going to have an dipole-induced dipole intermolecular bond. And this is just trying to show you how the temporary dipole is induced on this CS2. And so it can go ahead and connect with the partially negative end of the acetone. So like dissolves like, and unlikes don't dissolve. Okay. And if you've heard that before, we're actually talking about polarity. So polar substances typically dissolve in polar substances. Non-polar substances typically dissolve in non-polar substances, generally speaking. But defined dissolves. I mean, just a minute ago we saw something non-polar, Br2, dissolve in water. So polar substances don't generally dissolve in non-polar substances. So for the record, water's generally pretty darn polar, and it makes a good polar solvent. When you're dealing with things that have only carbon and hydrogen, hydrocarbons, there's not much polarity, so that's nonpolar. If you've got something kind of borderline, and I think we'll be talking more about some of that, but if you've got something kind of borderline, it's going to be a polar or nonpolar. It will behave like a nonpolar substance with regard to dissolving. This is an energy diagram, kind of from left to right. Think of it as kind of time along the x-axis. Along the y-axis, think of it in terms of energy. So I told you that we have to break the intermolecular bonds of your solute, okay, or this is the solvent. Break the intermolecular bonds of your solvent, break the intermolecular bonds of your solute. Both are endothermic. We're having to put energy in. So it's the old adage, as bonds are broken, energy is required. As bonds are formed, energy is released. So then on the other side, we see kind of the coming together process, the forming intermolecular bonds. We have 3 different scenarios here, and here they are. It could be such that actually the amount of energy released as the bonds are formed is less than the amount of energy required. And if that's the case, then this overall process is endothermic. Consistent with what we've been talking about in Gen Chem 1, if you have your delta H's are positive, it's endothermic. It's possible, we have two other scenarios. It's possible, this one, that actually the energy released by the bonds forming is greater than the energy required by breaking the bonds of your solvent and your solute. In that case, your overall process is exothermic, and you have a negative heated solution. That's delta H SOLN is heated solution. It's possible you have sort of a perfect ideal solution in which actually the amount of energy that was required to break the intermolecular bonds of the solvent and the solute is exactly equal to the energy that was released when new bonds were formed. That's, I think, an ideal solution. So when would you get an ideal solution? Well, if you have similar bonds being broken for your solute and solvent as are formed when they come together. Similar type. So when you either have an endothermic or exothermic overall process, then it's not an ideal solution. But if it is an ideal solution, we say that we'll be talking more about Raoult's law coming up. So non-ideal solutions simply mean it was endothermic or exothermic. Your heat of solution is not zero. More than likely, you're going to have an exothermic heat of solution where the energy that's released as your bonds are formed between your solute and solvents is greater than the energy that was required to break those intermolecular bonds. It's possible you may have an endothermic overall process. All right. So here we go. If we kind of look at these structures, to me, it's easiest to look kind of this semi-Lewis structure right here. It's kind of stick structure. Here we have something that is polar over here. So we have the partially negative oxygen, and actually this CCl3H is also polar. So this is an example of a dipole intermolecular bond. Well, I guess the point here was you would expect this to be more like an ideal solution, because to break the intermolecular bonds in their pure state would be similar to the bonds that are formed when you go ahead and make the mixture. All right. So some vocabulary. When we use the word immiscible, immiscible means it does not dissolve. Okay. In a minute, you're going to see miscible. So we have immiscible, miscible. Okay, immiscible, you would expect to see layers formed, but honestly, I go back to the Br2 and H2O. I mean, they formed layers in that third test tube, but to a certain degree, the Br2 did dissolve in the water. So they aren't going to dissolve if basically it's too hard to separate the pure solvent and solute. And when the new bonds are formed, there's not much energy going to be released, so they won't favor that. Miscible, a pair of liquids that are miscible are a pair of liquids that actually, or don't have to be liquids, but are things that have actually dissolved in each other. And again, like dissolves like. You don't get any layers, you get a homogeneous mixture. Solutions that are generally ideal are the ones, remember, where the amount of energy to break the bonds is equal to the amount of energy to form the bonds. It may or may not be ideal, even if the two liquids are soluble. So like dissolves like, and unlike don't dissolve. So I have some pictures here to kind of show you. On the next slide, I think we're going to talk about this too. This is antifreeze and water. And it's hard, like, I only see one thing there. Well, if you look closely, you'll see the Mickey Mouse water molecules, and you'll see the antifreeze, ethylene glycol. And again, think of what ethylene glycol, maybe I'll put diethylene glycol. It's like that. Where you can see it down here and also in this structure. You see the OH, hydrogen bond, hydrogen bond. You can see it here. There's a hydrogen bond, reaches a hydrogen bond. So these are definitely ethylene glycol, polar, water, polar. So there's no problem to dissolve the two. This, on the other hand, is a strange place to put water and oil. It's pretty glass. But here we have the dense water and the less dense oil. Oils in general are just hydrocarbons, arranged in different ways, different chain lengths of the carbons. So they are generally immiscible. If you take your oil and if you go ahead and take your carbon chain and make it shorter and shorter and shorter, that actually has effect on its ability to dissolve. All right, let's see what this one looks like. When I was in high school, I was kind of like an outsider, and I was like the oil particle. And it's not that, and the cool kids were the water particles, water molecules. It's not that, like, I didn't want to be a part of them. It's just that they were so connected to each other that I couldn't get in it. Because you figure that hydrogen bonding is very strong. So that's kind of, you can kind of think of that's what's going on in the background with oil and water not mixing.
Wait,
Yes.
About the ethylene glycol.
Yeah.
So, so according to like the equation for it, right, it looks symmetric, right? Like,
yeah.
You know what I mean? But like,
Yeah.
according to the non-polar, or
Yep.
water's polar, and that would mean that's polar.
Yep. So according to this, it looks real balanced. So these are hydrogens. And this is an OH, like that?
Right.
Okay. But spatially, that's not how. Actually, a carbon chain like this, a carbon that's bonded to 4 other things like this, is going to make a, and I'm going to kind of butcher it, but it's going to kind of go like, it's going to be bent.
Okay, so it has to be linear.
Right.
And how do you like know necessarily? It's the what was it?
Oh, the molecular geometry?
Yeah. Because I remember we did that, but I can't remember.
And the other thing about this, though, there's what we call, since there's no double bonds, there's like free rotations around these carbons. So, and I've oriented them in space this way, but they could also, you could have the hydroxyl groups on the same side too.
It's like sigma bonds, right? Is that what it was?
To know the hybridization will tell you kind of how things scatter, the electron pair geometry. So it's sigma bonds and lone pair electrons. Yep. I think in this might be kind of our makeup day on Thursday, but we'll talk a little bit about organic, a little bit about kind of organic chemistry, how things are laid out, and this will hopefully we'll kind of look at some structures, and that'll make more sense. I think a little bit ago, I bet you saw this where you had the carbon, and you had the chlorines, and you had the hydrogen. So kind of you probably say, well, this is lopsided. I know that the regions of positives and negatives don't coincide because that guy is different. Now, if that had been a chlorine, you're back to being balanced. So that's non-polar, okay, and this is a polar. I don't know, it's a question, but yeah, it does. They don't line up spatially. Your thinking is right. Just keep adding to it. So this is to kind of the hydrocarbons. I told you that oils are mostly carbon and hydrogen. Anyway, kind of different. Sometimes you have branching, but here this is kind of showing you some kind of non-branched oils, where the gray there are carbons and the white are hydrogens. So you can kind of see the sneaky little things. Those are your oil molecules. And then we have the water, which is less dense. And again, it's kind of like the water's like all hydrogen bonding. Like, dude, I'm not going to break my bond here and go and dipole, induced dipole when this is really strong, and that'd be pretty weak. So this does say, however, if you read the caption, it says if you want a solvent, now I don't think it's a very safe solvent. Carbon tetrachloride, I wouldn't spend a whole lot of time around it without like protective equipment and ventilation. But this would be great for oils. Why? Because it is nonpolar. Oils are nonpolar. I feel like we talked about this before, the whole inducing a dipole, whether you're successful or not. Remember that even if something's polar, it can have induced dipoles going on with it. But polarizability is a function, and basically we said that in general, if you get larger, whether you get a more massive atom with more neutrons and protons in its nucleus, more electrons, or makes it more polarizable, or literally if your molecule gets larger, it's more polarizable. So polarizability comes into play when we want to get some of those induced dipole action going on. Remember that the induced dipole and dispersion forces go together. Actually, I think on the slide that I had when I showed my different types of intermolecular bonds. Induced dipole, you're talking dispersion forces. So larger makes it more likely to temporarily get the electrons. It makes sense to me apart so that they could go ahead and temporarily have a partially negative, partially positive end. So we have water, and I think that could be O2. Okay. But if you want to dissolve water in O2, we saw a video of this a little bit ago. You need to go ahead and temporarily induce a dipole on that oxygen molecule. So once you, and to me, it's like which came first, the chicken or the egg? Almost the fact that we have this partially negative, to me it's pretty conceivable that we could go ahead and have the electron cloud disperse that way because this is partially negative. Electron clouds can go that way, it's partially positive. And then once it's partially positive, that's your induced dipole, you can go ahead and have an intermolecular bond there. Makes, of course, that end partially negative, which now it's just itching to bump up against a hydrogen of a water molecule. So that makes the whole inducing a dipole makes more sense if it's a mixture, I think, to me. So whether these are all gases. Methane, gases at normal atmospheric pressures and temperatures. Methane, oxygen, carbon monoxide, nitrogen, and helium. So can you dissolve them in water? Well, this is talking about the solubility in water. Notice there is a temperature component along the x-axis. But if we take any temperature, okay, you can take 10 degrees Celsius here, you can see that we definitely have a trend in solubility. I'm going to show you some molecular weights here in a minute, but the bigger the molecule, methane's the biggest, it's the most polarizable, so it's the most soluble. Helium, a tiny little atom, okay, relatively small, polarizability low, solubility low. So that's kind of, it makes sense. But another trend, and I can't remember, I think we're going to be talking about this at a different lecture in this same unit. But if your solute, the thing you're trying to dissolve, is a gas, and you're dissolving it in water, I guess that would be specific for water, notice that solubility decreases with increasing temperature. It just does. Okay. So this, I go back to the little fishies, and thinking of what they're doing this winter or what they're going to do this summer. Well, winter and summer brings with it two different temperatures and two different solubilities of oxygen. So you figure they can be pretty feisty when you're talking, this is Celsius temperature, so the water is still liquid. When you're talking 5 degrees Celsius, they have a lot more oxygen potentially dissolved in their environment than they do at 26 degrees. So go fish go. Didn't get my pole out at all last year, and I'm hoping to this year, so we'll see. So this table goes along with that previous figure. So well, we have the lightest on top, the heaviest on bottom, hydrogen molecule, nitrogen molecule, oxygen molecule. In terms of how many grams of that solute you can get to stay in 100 grams of water at 20 degrees Celsius, this is what you're looking at. So again, we increase size, we increase solubility. So it's more polarizable. But by golly, to get those to dissolve in water, you're talking about induced dipole intermolecular bonds having to be formed. Wow, I talk real fast. So actually we have 4 things here. The 2 layers, we have carbon tetrachloride, which is nonpolar. In the top one, we have forced, or somebody forced, I2, molecular I2, which is nonpolar, to go ahead and dissolve to a certain amount in polar water. I think this is kind of interesting. But you figure the I2 didn't want to be, since the I2 is nonpolar, it didn't want to be with water. It really wanted to be with the carbon tetrachloride. So given a choice, you go ahead and you shake it up. Again, let your get your 2 layers of the polar water and the nonpolar carbon tetrachloride, and by golly, your I2 is going to favor hanging out with the nonpolar carbon tetrachloride. I don't know, I guess it's not captioned here, but the reason your I2 has 2 different colors, I can't remember. There's a reason for that. I'm drawing a blank right now. I think this video just does the same thing. Points. You will need to be able to look at Lewis structures like this and to know just kind of like what you do for your lab and writing up for the the heats of evaporation or the cooling evaporative cooling. So you'll need to know, like, this is polar, nonpolar, and nonpolar. So simple molecules. This one, and hopefully it'll reinforce when we talk about organic molecules, but what hopefully hit you over the head with this one was kind of what I focused on, was the ability to hydrogen bond, not so much the structure of it. And a few slides ago we had, I don't know if this will help you, but was it acetone has this? I might be butchering it. Well, I don't think this is acetone. But that, you might say, I go back to your symmetry thing, you're like, oh, that's pretty symmetrical. But hopefully you would see actually, this one throws us off because we think hot dog, right? This one looks like a hot dog with a little bit of cheese or something coming up there. And so this one definitely, it's polar. Because the regions of negatives and positives do not coincide. Okay. So I was so worried about getting through those 40 slides. Oh well. I really wanted to, and I really did. So I'm not going to go on to the next part, but we shall see.